folks, it's April 20th, about 1:36 in the afternoon as I start this video. Very short video today, problem set. We're just going to look at 4 universal wave equation problems, and then you'll have a little bit of follow-up on that. Now, you don't have a copy of these problems. However, I did include a PDF sample in your assignment through Google Classroom. So hopefully you can make that work, or just study the examples. The PDF version of the solution guide is also there to get through today's bell work. First thing to keep in mind that anytime we're talking about light, EMR, in air or in a vacuum, the speed of it's going to be 3.00 times 10 to the 8 meters per second. That's a constant. Sometimes we use the letter V, sometimes we use the letter C to tell us that we're talking about the speed of light. Now we're also going to do a couple of questions today, today's sample with sound, even though this is an EMR chapter, just to do a little comparison. The speed of sound is about 343 meters per second in air, but that is not a constant. The density of the air can change that quite a bit. So we'll see that that's different, but as you work through the bell work today, make sure you keep in mind speed of light, 3.00 times 10 to the 8 meters per second. So let's take that forward to the first question here. You remember that X-rays have a high frequency and extremely short waves. A particular X-ray has a frequency of 3.00 times 10 to the 16 hertz. How long is one of these waves? To solve for this, we're going to use what's called the universal wave equation. When it comes to universal wave equation, V is always equal to F times lambda. So F stands for the frequency. It's the number of waves to pass a fixed point per second. And wavelength is the distance from crest to crest or trough to trough to the same spot, the second wave, the wavelength, the length of one wave. So we're looking for how long is one of these waves. So we're looking for wavelength. So we have to rearrange this for lambda equal to V over F. The speed of the wave, 3.00 times 10 to the 8 meters per second. Hey, that wasn't given in that question. How do I know that? We established if we're talking about any type of EMR, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, or gamma, we're talking about EMR. It all travels at that speed in air in a vacuum. So then we just take the frequency, which was given as 3.00 times 10 to the 16 hertz. Let's fire up the old calculator. 3 second exponent 8 divided by 3 second exponent 16 equals 1.00 times 10 to the minus 8 meters. So it's a very, very small wave in the X-ray range. High frequency, short wave. Take a few seconds, study that over, maybe just write it down on loose leaf if you can't print the samples, and you can compare it up later. So we're going to switch out of EMR to sound waves for this question. And we're saying that they're traveling at this many meters per second. That, of course, is the V. It tells us the wavelength is this. That's wavelength. We want to find the frequency. So we're going to use our basic universal wave equation. .43 meters per second is about the speed of sound under normal circumstances, normal density of air, but with different humidity, different density, it's going to speed up and slow down. Interestingly enough, the more dense a medium is, so as we start shining light into water, to glass, it slows down. But in terms of sound, if you put it into a more dense medium, it speeds up. So it's kind of a little bit different. It's interesting. So on the calculator, 343 divided by 13.7 gives us a wavelength, gives us a frequency of about 25.0 hertz. Take a couple minutes to copy that down. Remember, that's sound. It's not EMR. Question number 3 is much like question number 1. They're both dealing with X-rays. So, particular X-ray this time, instead of 3.00 times 10 to the 16, still in that 16 range, but it's 3.12 times 10 to the 16 hertz. How long is one of these waves from crest to crest? So we want the wavelength again. Start with the base formula. V equals F times lambda. Rearrange for lambda equals V over F. I know the speed of light of EMR, all types in air in a vacuum, is 3.00 times 10 to the 8 meters per second. But if you don't know it, it is in your Alberta Head formula sheet, so make sure you have that handy. Pull out the calculator for this. 3 second exponent 8 divided by 3.12 second exponent 16. Enter. 9.62 times 10 to the minus 9. So it's a little bit smaller than the question number 1. Good. Take 2 seconds and copy that down. One more question to do. So we're going to do another sound question. Sound waves have a wavelength of 12 meters and frequency of 28.3 hertz. What's the speed of the sound wave? What is the speed of that sound wave? That sound wave. Do I stutter? Apparently I do. So this is just a V equals F times lambda. It's not light, so it's not the 3.00 times 10 to the 8. The frequency here was given as 28.3 hertz times the wavelength, which was lambda 12.0 meters on the calculator. Oh, just a little bit more. There we go, clear. 28.3 times 12. 340 hertz. When we move that, round that to 3 sig digs. So it's moving a little bit slower, which indicates slightly less density than normal day. That's it for this, folks. Holy cow, record time, 8 minutes. Take care and stay well.